This is the motivation for that so called quote unquote peculiar choice of H 1. Now, we see things falling in place. The Z inverse was required to bring this complex conjugation, replace omega by minus omega. And of course, as you see, for a real impulse response, it had no effect on the magnitude, but we could remove the phase. So, it is a strategic choice of analysis high pass. You could have chosen H 0 minus Z or something like that, but you chose H 0 minus Z inverse because you wanted that complex conjugation. And then you put a Z raised to the power minus D because you wanted to make it causal. So, Z raised to the power minus D is to introduce causality. The Z replaced by Z inverse is to bring in this complex conjugation, to bring in power complementarity. And finally, the minus Z inverse instead of just Z inverse is to convert the low pass to a high pass. So, now it all falls in place and we have justified our choice. And now, we also know what we demand of H 0 Z, so that we get perfect reconstruction. Let us look at that condition once again. That condition tells us, and let me write it slightly differently. That condition tells us for perfect reconstruction, some interesting intermediate filter, which we shall define by kappa 0 z. So, let us define kappa 0 z as H 0 z H 0 z inverse. What we are saying is that for perfect reconstruction, we require kappa 0 z plus kappa 0 minus z to be a constant. Now, things are beginning to make even more sense. If we know the sequence that gives us H 0 z, what is the sequence that gives us H 0 z inverse? Let us reflect a minute on this. So, what I am trying to say is, we have agreed that we are going to choose even length H 0 z, something like an impulse response of the following form: H 0, H 1 and so on. H 0 lies at 0 up to H d. Remember, d was odd. And therefore, H 0 z inverse would then correspond to the following. Quite clear. When you replace z by z inverse, you are essentially reflecting the sequence about the point n equal to 0. Simple. Now, H 0 z times H 0 z inverse corresponds to their convolution. You know, when you multiply two z transforms, the corresponding sequences are convolved, and therefore, we have this convolved with this. Maybe I should put parenthesis here and indicate the 0 clearly there. Now, how do you convolve? Well, these are of equal length, so I could choose either of them as the static one and the other one as the moving one. So, just for convenience what I will do is the sequence which we started with, the one corresponding to H 0 we shall keep as the static sequence, and the one corresponding to H 0 Z inverse we shall make it move. Now, what we are saying essentially is keep this static. So, you have and make this move. So, when you make the other one move, you are doing two things. You are bringing, you see, you want to, if essentially you have sequence 1, let us say sequence, let us call that sequence G n just for the time being. The sequence G n is this, or G k if you like. In which case the sequence G n minus k, this is of course a function of k. So, k equal to 0, it is H 0 and so on. So, G of n minus k is going to look like this, the 0 would go to n, and whatever comes before 0 would go after n there. So, you have H 1 and so on up to H d. So, this reaches the point n plus t here. This is the sequence G n minus k, and this you may of course call the sequence H 0 of k if you like. So, you are trying to convolve this sequence with essentially with this sequence, but in that convolution you are going to move around this at different locations here. Now, visualize, let me put that down clearly once again for you. We are saying we have this so called static sequence, and this is going to move around. N is moving. So, you can visualize the situation. For different values of n, this lies at different locations with respect to the static sequence. For example, when n is equal to 0, the samples actually coincide. When n is equal to 1, then H 0 clashes with H 1, and of course, H d has gone out of range. So, it has gone to a 0 sample here. When n is equal to minus 1, you are here, and then of course, H 1 clashes with H 0 H d with H of d minus 1 here, and so on and so forth. So, you see what we have is actually the dot product of the sequence and its own shifted versions. This is very interesting. What we are saying is that the samples of kappa 0 are actually dot products of the original filter impulse response shifted by different amounts of shift. Let us write that down, that is a very important conclusion. Kappa 0 z, which is H 0 z times H 0 z inverse, corresponds to a sequence whose nth sample is as follows: the dot product of the impulse response corresponding to H 0 and the same shifted by m samples. If you want to be very specific, you should say m samples forward, but that does not really matter. So, if you want to write it down in the notation of dot products, what we are saying is that this denotes the dot product of sequences A and B. So, A with an argument, integer argument, B with an integer argument. This is the dot product of A and B. And we are saying the nth sample of the filter kappa 0 is essentially the dot product H 0 and H 0 shifted by m. Plus or minus is not really an issue. If you like, you can make this minus. There is a symmetry. You can visualize that. If you shift backward by 2 or forward by 2, it is the same. Let us verify that for a length 4, for example. You will see what I mean. So, if you had a length 4, for example, you would have H 0, H 1, H 2, H 3, and if you took this and the same thing shifted by 2, you are talking about this dot product. The rest of it is 0, of course. So, here again you get zeros and you do not need to write that. So, the dot product is essentially H 0 H 2 plus H 1 H 3. Now, if you were to shift it backwards, so you had H 0 H 1 H 2 H 3 there, and you shifted it backwards, and of course, this is all 0. So, again the dot product would be H 0 H 2 plus H 1 H 3. So, as you can see, shifting backward or forward by m is not an issue. However, what we are saying here is something very interesting. We are saying that with this understanding of the samples corresponding to kappa 0 z, kappa 0 z plus kappa 0 minus z is a constant, and if we take the inverse z transform now, and if we only care to multiply by half on both sides, this is also a constant, obviously, and this is something very familiar to us. We have encountered this when we did downsampling. So, in fact, if the original sequence corresponding to kappa 0 z, so let kappa 0 z correspond to the sequence, let us write small k 0 n. Then what we are saying is that when this sequence is modulated by a sequence which is 1 at the even locations and 0 at the odd locations, so, it is something interesting we are doing. We are modulating this kappa 0 n by a sequence which is 1 at the even locations and 0 at the odd locations. This gives us a sequence corresponding to the inverse z transform of a constant, which is essentially an impulse. Now, this modulation is what we derived when we talked about the z transform across a downsampler. So, remember, when we go across a downsampler by a factor of 2, it is like first modulating by a sequence which is 1 at the even locations and 0 at the odd locations. In general, when you go across a downsampler by a factor of capital M, it is like modulating with a sequence which is 1 at all multiples of capital M and 0 elsewhere, followed by an inverse upsampling operation. So, remember, a downsampling by 2 was modulation by a periodic sequence with period 2, which was 1 at locations equal to multiples of 2 and 0 else, followed by an inverse upsampler by a factor of 2. Inverse upsampler means a compressor, throw away the zeros. Downsampling by a factor of m was essentially multiplication by a periodic sequence, period capital M, 1 at all multiples of m, 0 elsewhere, followed by an inverse upsampler by a factor of capital M, which means throw away the zeros and compress. So, you see that throwing away the zeros was what made z replaced by z raised to the power half. So, here in this expression kappa 0 z plus kappa 0 minus z, we are not writing z raised to the power of half. So, we do not do that inverse upsampling operation, but the rest of it is there, and that is the justification for this step here, modulation with this periodic sequence. And now, this is equal to a constant, which means if we take the inverse z transform here, we are saying this is essentially the impulse, which means this has a non-zero value at 0, but 0 everywhere else. So, let us write that down. Kappa 0 n, when modulated with this periodic sequence with period 2, with the ones at multiples of 2 and 0 elsewhere, results in a sequence which is non-zero only at z equal to at n equal to 0. That is what we are saying. And obviously, at the odd locations anyway it is 0. So, there is nothing very surprising here. It is at the even locations that we have a surprising result there. So, the surprise is at the even location. Of course, m not equal to 0. So, what we are saying is that if I take the impulse response of the low pass filter on the analysis side, shift it by any even number of samples 2, 4, minus 2, minus 4, 6, minus 6 and so on, and take the dot product of that shifted impulse response with the original impulse response, that dot product is 0. For those of us who are familiar with the idea of autocorrelation, what we are saying is that the autocorrelation of the impulse response of the low pass filter is 0 at the even locations other than 0. Now, let us use this to build the first of the family of Dobach filters. So, you see, well, I should say first non-trivial. So, it is second in that sense, the first non-baby member. Dobach filter with length 4. Is going to look something like this. It is going to have an impulse response H 0, H 1, H 2, H 3. And recall what we did yesterday. We said that in this filter, we would need to bring in one more factor of the form 1 minus z inverse in the high pass filter. So, Har had 1 minus z inverse in the HPF. So, this length 4 filter would have two factors, 2 1 minus z inverse in the high pass filter. And that means, you see, the high pass filter was obtained by replacing z by z inverse and then by minus z as well. So, if the z inverse part gets taken care of by the delay z raised to the power minus d, but the z replaced by minus z needs to be undone to go to the low pass, and therefore, the low pass filter would have a factor 1 plus z inverse squared. Now, when you say it has a factor 1 plus z inverse the whole squared, you have already constrained 2 of the 3 zeros that it has free to be chosen. What I mean is, if you looked at h 0 z, it would have been h 0 plus h 1 z inverse plus h 2 z raised to the minus 2 plus h 3 z raised to the power minus 3. So, there are 3 zeros to be chosen. Out of them, we have already chosen 2. So, we have only one free. Let that free one be at b 0. So, in all, it is very simple. We can take h 0 z to be of the form 1 plus z inverse the whole squared times 1 plus b 0 z inverse. What do we have then? Let us expand this. We have h 0 z is essentially 1 plus 2 z inverse plus z raised to the power minus 2 times 1 plus b 0 z inverse. And we can expand this further. That product will be 1 plus 2 z inverse plus z raised to the power minus 2 plus b 0 z inverse times this. So, b 0 z inverse plus 2 b 0 z raised to the power minus 2 plus b 0 z raised to the power minus 3. So, in a sense we have the following impulse response for the filter: 1, 2 plus b 0, 1 plus 2 b 0 and b 0 here. This is the impulse response. Now, we have set up the low pass filter for the second member in the Doobash family. Where do we go from here? We shall use the constraint that we just derived, namely that the dot product of this impulse response with its shifts by even shifts must be 0, and we shall see the constraints that emerge on the free parameters. In the next lecture, therefore, we shall constrain the value of b 0, make a choice for b 0 and derive precisely the impulse response of the Doobash second member, and thereby also establish a general procedure for building up the Doobash family low pass filters. Concurrently, we shall explain how this family evolves and recall again the significance of going from one member to the other. With that, then, we shall conclude the lecture today. Thank you.